Hi, welcome to Term Science. Today's topic is about perfect and imperfect intercooler on gas turbine engine. We know that intercooler is a device which is placed between two compressors. The purpose of intercooler to reduce the temperature of air so that the work given to the compressor will reduce. Here we can go for either air cooling or liquid cooling. It is depends upon application. In this lecture, we will discuss what is the advantage and disadvantage of perfect and imperfect intercooler on gas turbine engine. For that, before we need to know what is meant by perfect intercooler, what is meant by imperfect intercooler. Let's discuss. We know that initially the compressor sucks air from the atmosphere and compress isentropically where the pressure and temperature of air is increased. Later, this air sent to the intercooler where the temperature of air is removed. In such a way, if it is perfect intercooler, the outlet temperature of intercooler should be equal to the inlet temperature of compressor. That is T1 is equal to T3. Then it is called perfect intercooler. Whereas we know, right? If it is not equal, then it is called imperfect intercooler. That is, the outlet temperature of intercooler never be equal to the inlet temperature of the compressor. Then it is called imperfect intercooler. Now we will discuss how to find out the intermediate temperature of the intercooler. That is P2 or P3. We know that it is constant pressure heat rejection. So we need to find out P2 or P3 because P2 is equal to P3. For that, we know that the work given to the compressor, that is the total work given to the compressor, that is work of first compressor plus work of second compressor, that is WC1 plus WC2. We already found out by using the steady flow energy equation, that is first law of thermodynamics. So WC1 is equal to Cp T2 minus T1. Similarly, WC2 is equal to Cp T4 minus T3. Substitute in above equation Cp T2 minus T1 plus Cp T4 minus T3. This is for isentropic compression, that is reversible adiabatic. If you are considering actual compression, then we have to consider the efficiency of compressor, that is Wc is equal to Cp T2 minus T1 divided by first compressor efficiency plus Cp T4 minus T3 divided by second compressor efficiency. To simplify this equation, take T1 outside from here, T3 outside from here. That is Wc is equal to Cp T1 divided by first compressor efficiency T2 divided by T1 minus 1 plus Cp T3, take T3 outside, divided by second compressor efficiency T4 divided by T3 minus 1. We know that from adiabatic expression T2 divided by T1 is equal to P2 divided by P1 whole power gamma minus 1 divided by gamma. Similarly, T4 divided by T3 is equal to P4 divided by P3 whole power gamma minus 1 divided by gamma. Just substitute this equation in above equation. You will get it Cp T1 divided by first compressor efficiency P2 divided by P1 whole power gamma minus 1 divided by gamma minus 1 plus Cp T3 divided by second compressor efficiency P4 divided by P3 whole power gamma minus 1 divided by gamma minus 1. To simplify this equation, let's take gamma minus 1 divided by gamma as x. Then T3 divided by T1 is equal to R. So that this T3 can be replaced as TR into T1. Substitute in above equation, you will get it Cp T1 divided by first compressor efficiency P2 divided by P1 whole power x minus 1 plus Cp, instead of T3 you can write TR into T1 divided by second compressor efficiency P4 divided by P3 whole power x minus 1. Again simplify this equation, Wc is equal to Cp T1 divided by first compressor efficiency P2 whole power x dot P1 minus x minus 1 plus Cp Tr T1 divided by second compressor efficiency P4 power x dot P2 power minus x minus 1. Why we written P2? We know that P3 is equal to P2. Here also we have P2. So we consider P3 is equal to P2. So what we need to find out? We need to find out intermediate temperature. So we have only one unknown. So let's go for ordinary differential equation. That is d by dP2. So we are going for P2 CPT1 efficiency of compressor 1 P2 power x dot P1 power minus x minus 1 plus CPTRT1 divided by second compressor efficiency into P4 power x dot P2 power minus x minus 1 is equal to 0. So after differentiation, you will get it CPT1 divided by first compressor efficiency. This P2, we are differentiating only to P2. So x dot P2 power x minus 1. We are not differentiating P1. So P1 whole power minus x will be there. This will be constant. So we are not considering it. Plus CPTRT1 divided by second compressor efficiency P4 power x. See again P2 we have, we are going to differentiate minus x P2 power minus x minus 1. Again constant is equal to 0. So here we have minus x, here we have plus. So this equation can be written as CPT1 divided by first compressor efficiency x P2 power x minus 1 dot P1 power minus x is equal to minus become plus CPTRT1 divided by second compressor efficiency P4 power x dot x P2 power minus x minus 1. So you can see here CPT1 we have it right side, and similarly here also we have left side. So CPT1 will get cancelled. Similarly x and x will get cancelled. So this equation can be written as P2 power x minus 1 dot P1 power minus x is equal to, let's send this efficiency that side. So this becomes efficiency of first compressor divided by efficiency of second compressor into TR. We have TR P4 power x dot P2 power minus x minus 1. So rearrange this equation, we will get it P2 power x minus 1 divided by P2 power minus x minus 1 is equal to efficiency of first compressor divided by efficiency of second compressor into TR P4 power x divided by P1 power x. So this equation can be written as P2 power x minus 1 plus x plus 1, which means a power m divided by a power n is equal to a power m minus n. So minus minus become plus is equal to efficiency of first compressor divided by efficiency of second compressor into TR. So P4 power x dot P1 power x, because we taken into numerators. So this equation can be written as P2 power 2x. How it came? X become 2x minus 1 plus 1 will get cancelled. Is equal to efficiency of first compressor divided by efficiency of second compressor into TR. This P4 into P1 whole power x. So this x will get cancelled. Then P2 whole square is equal to efficiency of first compressor divided by efficiency of second compressor into TR power x, because we are not having x, into P1 into P4. So P2 is equal to, this is the final equation, root of efficiency of first compressor divided by efficiency of second compressor into TR. Already we know what is the x here. X is equal to gamma minus 1 divided by gamma P1 into P4. So now this equation can be used. This equation can be used when we have imperfect intercooler. So what to do if it is perfect intercooler? Let's take for perfect intercooler, this TR become 1. We know T3 divided by T1 is equal to 1 because T3 is equal to T1. Let's assume the efficiency of first compressor is equal to the efficiency of the second compressor. Then this equation becomes P2 is equal to root of P1 and P4. In last class, we have discussed this equation. From these two equations, we can conclude that when it is imperfect intercooler, temperature ratio plays a major role, so that this P2 will be higher compared to the perfect intercooler. In next lecture, we will discuss what is the effect of imperfect intercooler on gas turbine engine. Thank you.